The easiest story to tell about artificial intelligence and power is that artificial intelligence only needs more electricity. That story is not wrong. It is just too simple. Electricity matters. Data centers need power. New clusters need sites, utility coordination, delivery equipment, cooling, and operating budgets. If the power system cannot support the load, the model never becomes useful at scale. But the deeper constraint is not just whether enough megawatts exist somewhere on paper. The harder question is whether nominal power can become reliable compute. Installed megawatts are not the same as deployable compute. That is the central distinction. A site can have a headline power number. It can have a contract, a plan, or a public announcement. It can appear large enough to support a new generation of artificial intelligence systems. But a headline number is only the beginning of the conversion problem. Power has to move through a dependency hierarchy before it becomes work the system can actually perform. That hierarchy is not a universal construction sequence. It is a set of dependencies. Each layer determines, enables, limits, or conditions how much upstream capacity becomes usable downstream capacity. Nominal or installed electrical capacity has to become contracted power. Contracted power has to be supported by interconnection availability. Interconnection has to lead into facility delivery capacity. Facility delivery has to become rack-level, usable power. Rack-level power has to be matched with cooling, telemetry, commissioning, scheduling, and reliability controls. Only then does the system approach deployable compute capacity. And even then, only part of that capacity becomes workload serving compute capacity, the portion actually available for real workloads after software, model placement, scheduling, service level, and operating constraints. Deployable compute is compute that can be brought online and operated. Workload serving compute is the usable part that can actually serve real work under the constraints of the operating system around it. That distinction changes how we should read artificial intelligence infrastructure announcements. A megawatt total is not the same as a running cluster. A running cluster is not the same as a dependable service. A dependable service is not the same as realized compute output. Between those stages sits the practical engineering of delivery, placement, heat, monitoring, scheduling, and reliability. Interconnection is part of the story, but it is not the end of the story. Grid access is a necessary upstream condition. If power cannot be connected, timed, or delivered to the site, then the downstream system cannot operate. But once that boundary is crossed, the next constraint moves inside the delivery system. The question becomes whether the facility can turn power access into usable artificial intelligence capacity. That is why the episode should not stop at the grid edge. The conversion continues inside the site. Facility delivery capacity has to support the equipment that is actually being deployed. Rack-level usable power has to match the density of the hardware. Cooling has to remove the heat created by concentrated compute. Telemetry has to show what the system is doing in real time. Commissioning has to prove that the delivery chain works as an operating system, not just as a design drawing. Scheduling has to decide which workloads run, when they run, and how they respond when power or thermal conditions change. Reliability controls have to keep the system from turning a local failure into a wider operating event. This is where the architecture question becomes important. Artificial intelligence loads are not only larger, they can be denser, more dynamic, and more thermally demanding. Rising load density puts pressure on rack and facility distribution designs. Rapid load transients can stress delivery equipment and operating controls. Thermal stress becomes part of the compute story because heat is one of the ways nominal capacity fails to become usable capacity. The point is not that one new architecture has already solved the problem. The point is more disciplined than that. Traditional rack and facility distribution architectures are under pressure, and emerging directions are being explored. But those directions should not be treated as settled industry-scale answers simply because they appear in technical discussion. The constraint is real. The mature answer is still being worked out. That is why deployable capacity is a systems concept rather than a procurement claim. A company may be able to buy hardware. It may be able to reserve power. It may be able to announce a site, but the operating question is whether the full chain can support the hardware generation, density mix, cooling plan, placement policy, scheduling model, and reliability target required by the workloads. Flexible compute belongs in this picture, but it also needs discipline. Scheduling and telemetry can make compute load more responsive. A cluster can be operated in ways that reflect power conditions, workload priority, performance targets, or carbon-aware timing. That makes the compute stack more flexible than a simple, always-on load. But flexibility does not erase physical delivery limits. A workload can move in time only if the service allows it. A load can be reduced only if the application, users, contracts, and reliability targets can tolerate the reduction. Telemetry can reveal constraint checks. It needs logs. It needs auditability. It needs a record of when the model was used, what context it saw, what output it produced, who reviewed it, and what happened next. Otherwise, the organization has activity but not reliable capacity. Cost is part of this conversion as well. Intelligence that is technically available can still be economically unavailable. High-quality inference may be too expensive for low-margin tasks. Latency may be too slow for real-time operations. Hardware may be reserved for higher-priority workloads. Rate limits may appear at exactly the moment demand rises. In that situation, the institution does not have the capacity it thought it had. It has access under favorable conditions. A similar limit appears when teams try to scale from one successful use case to many. The first workflow may have a patient expert, a clean data source, and a narrow decision boundary. The 10th workflow may not. It may involve messy records, conflicting incentives, unclear ownership, and users who do not understand what the model is good at. Each expansion asks the same question again: is this still deployable capacity or only transferred enthusiasm? That is why throughput has to be measured honestly. It is not just the number of prompts processed or documents generated. It includes review time, exception queues, rework, escalation, downtime, security review, user training, and the cost of correcting mistakes. If those hidden loads grow faster than the model's contribution, the apparent capacity disappears inside the operating system around it. That distinction may matter more as artificial intelligence moves from experiments to recurring work. A demo can succeed once. A department needs the system to work every day. A regulated institution needs the system to work under documentation, audit, and review. A production environment needs the system to fail visibly, recover gracefully, and avoid turning small errors into large operational events. This is why deployable capacity is not the same as automation. The simplistic story says that more capable models will automate more work. Sometimes they will. But the more important question is where automation can be trusted, governed, afforded, and integrated. In many high-value settings, the result may not be full automation. It may be supervised throughput, more cases reviewed, more anomalies detected, more drafts prepared, more options compared, more evidence organized, more decisions supported. That is still capacity, but it is capacity shaped by controls. The advantage in this phase may not simply go to institutions with access to the strongest models. It may go to institutions that can turn intelligence into dependable operating capacity. That means they will understand their workflows. They will know which tasks are ready, which are not, and which require validation before expansion. They will build feedback loops instead of relying on one-time pilots. They will treat security and governance as part of deployment, not as paperwork after deployment. They will measure throughput honestly, including review time, exception handling, compute limits, and failure recovery. They will not ask only, can the model do this? They will ask, can our system absorb this safely, repeatedly, and at a cost that makes sense? That question changes the map. It moves artificial intelligence away from a capability race alone and toward an operating capacity race who can safely turn intelligence into usable work. It makes integration talent more important. It makes validation infrastructure more important. It makes inference economics more important. It makes governance practical rather than ceremonial. It makes human review a design problem. It makes reliability visible. And it explains why many impressive demonstrations do not immediately translate into institutional transformation. The missing piece is often not intelligence. It is the deployable capacity around intelligence. A model can answer, but the institution must decide when the answer is allowed into the workflow. A model can draft, but the organization must decide who owns the draft, what standards it must meet, and where it can be used. A model can search, classify, summarize, recommend, or monitor, but the system must decide what counts as success, what counts as failure, and what happens when the model is uncertain. Those decisions are infrastructure. Not all infrastructure is physical. Some of it is electrical, thermal, and computational. Some of it is procedural, legal, and organizational. Some of it is the quiet discipline of logs, permissions, review queues, escalation rules, and budget limits. Together, those layers help determine how much artificial intelligence an institution can actually use. That is one of the constraints after intelligence, not whether useful capability exists in principle. Whether that capability can be delivered into the real world as safe, reliable, affordable, governed, integrated capacity. The next phase will still reward better models. But better models will not be enough by themselves. In many settings, the practical advantage may come from the deployment layer, the ability to convert capability into throughput, throughput into trust, and trust into sustained institutional output. In that sense, deployable capacity is not a side issue. It is where artificial intelligence becomes real. If this helped you see the next constraint more clearly, subscribe to Quantum Convergence. AI will keep tracking where artificial intelligence meets the systems required to make it real.